Okay, 5.10 is the introduction to optimization. To optimize is to make the best or most effective use of a situation or resource. So here are some strategies for solving optimization problems. We have draw a picture, identify the known and unknown quantities, write an equation that will be optimized, write your equation in terms of a single variable, determine the desired max or min values with calculus techniques, and determine the domain or endpoints of your equation to verify if the endpoints represent a max or a min. So when we talk about these topics, these first three are what we're going to mainly focus on for this section of 5.10. And those last two, we're going to spend more time on that on 5.11, so on the next notes. So number 1 says, find two numbers whose sum is 30 and whose product is as large as possible. So two numbers whose sum is 30. Okay, so we're going to do x plus y equals 30, where we're allowing x and y to be two numbers. Which means if we were to solve for y, we have y is equal to 30 minus x. Okay. And then it says whose product is as large as possible. We'll let P equal the product of x times y, and let's plug in y. So we have P is equal to x times 30 minus x, which gives us 30x minus x squared. Okay. This makes sense because if we want something that is as large as possible, what we're finding is the maximum. And when we have a negative quadratic like that, we know that we are going to be given the maximum right at the top. Okay. So, so in order to find those two numbers, we would have to solve for x. Well, in order to find two numbers, x, I think for this first one, it just wants us to find that equation. Okay, so we're just finding that equation. If we were to find those two numbers, then we would set this equal to 0, find the possible x values. Once we have those possible x values, then we plug them back into the equation for y, and we would have all the points where we would find the two numbers that give us the sum of 30 and the product that is as large as possible. But here, it looks like we're just focusing on number 2 in the strategies, which is write the equation. Okay. Number 2 says, what point on the graph y is equal to the square root of x is closest to the point 5, 0? Okay. So in order to find this, what we need to do is we need to first identify this as a point. So y is the square root of x, which means 2. Okay, so we know y is equal to the square root of x. Well, let's go ahead and use this point right here. Okay, well, in this point, this is 2, 4. So if we're using this point to optimize what our x value is, if y is the square root of x and y here is 4, well, the square root of 4 is our x value too. So what we're really seeing is that x comma y can be written as x comma square root of x. Okay, so we're using that point to optimize what our x value is based off the given information that y is equal to the square root of x. Now what we need to do is we need to find this distance here. And we do that using the distance formula. Okay, so recall that the distance formula is D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, here our 2 points that we're going to be using is this, the x and the square root of x, and then also the point we're trying to get closest to, which is 5, 0. So plugging everything in, we have D is equal to the square root of x minus 5 squared plus the square root of x minus 0 squared, which we can simplify that to the square root of x minus 5 squared plus x. Okay, so in order to find what point on the graph is closest to that 5, 0, what we would be using would be this distance formula here that shows us the distance between our given point x, square root of x, to our point we're trying to find, which is 5, 0. So all we're doing here is setting up the equations. We're not solving just yet. Okay. Number 3 says Mr. Kelly needs to make an open top box to store all his magic cards. He has a piece of cardboard that is 14 by 30 inches. To do this, Mr. Kelly cuts out squares of equal sizes from the 4 corners so the 4 sides can be bent upwards. What size would the squares be in order to create a box with the largest possible volume? So again, we're not solving. We know that we are trying to find the maximum because it says the largest possible volume. So we're just going to draw our image and set up our equation. So, okay, here's a box. Okay, they said the box is going to be 14 by 30. And then they are cutting out each of the corners equal size squares. So we can just label all of this X. Okay, so in order to find volume, we know volume is equal to length times width times height. So in order to find the volume in this case, our length, which is 30, is actually going to be subtracting 2 of the x's because of these right here. So we have 30 is this entire thing, but we need to subtract this x and this x. So it's 30 minus 2x, okay? Our width is going to be the same. So we have 14 and we are taking out both the corners. So 14 minus 2x. And then our height is the height. If we fold up each of those corners where they cut them out, we'll notice that our height is just x. Okay, so simplifying this, we would have to FOIL. Okay, so what I'm going to do first is I'm going to do v is equal to 30 minus 2x, and then I'm going to distribute that x in, so I have 14x minus 2x squared. And then I am going to FOIL this together. So I have v is equal to 420x minus 88x squared plus 4x cubed. Okay, and in order to find that largest possible volume, that maximum, we would set this equal to 0 and solve. But we're not doing this. We just drew our diagram and we found our equation. Okay, last example. Yes, last example says 2 towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. There is a stake in the ground between the towers. The top of each tower has a wire tied to it that connects to the stake of the ground. Where should the stake be placed to use the least amount of wire? Okay, least amount of wire. So now we're talking about the minimum. Okay, so first we draw our diagram. Okay, if we're able to, we always draw our diagram. So we have 2 towers that are 30 feet apart. Here's one tower and here's the other tower. One is 28 feet tall and the other is 12 feet tall. Okay, There is a stake in the ground between the two towers. The top of each tower has a wire tied to it to the ground. So here's a wire and here's a wire, all tied to that one spot on the ground. Okay, so here's our diagram. So in order to find this, we have to find the length of the wire. So we have the length of this part of the wire, let's say L1, and the length of this part of the wire, which is L2, which means the length of wire is equal to L is equal to L1 plus L2. Because we don't know those lengths, we're trying to find the length of each of these that would require the least amount of wire. Okay, if we were to, let's see, if we were to try to find that length of each of them, notice how we have two right triangles, okay? And the length of each of them is the hypotenuse of each of the triangles. So in order to find that, we would have to use the Pythagorean theorem to solve, okay? So for the first one, we would have length 1 squared is equal to 28 squared plus x squared, because we're going to label this distance right here x. Okay, and then length 2 squared would be equal to 12 squared plus 30 minus x squared. So if we're labeling this part x, that means this part, since the whole thing is 30, is going to be 30 minus x. Okay, then we would solve for each one. So we would have length 1 is equal to the square root of 784 plus x squared, and length 2 is equal to the square root of 144 plus 30 minus x squared. Notice I didn't simplify anything. I just took the square root of both sides to try to find length 1 and length 2. Okay? So now that we have length 1 and length 2, we know that our formula for L, which is the total length of each of them, is going to be length 1 plus length 2. So L is going to be equal to the square root of 784 plus x squared, okay, plus the square root of 144 plus 30 minus x squared. Okay, and that is my equation. So again, in these notes, we are only focusing on the first three strategies, which is draw a picture, write an equation, and then write your equation in terms of one variable. And that's what we did. If we could draw a picture, we drew a picture. And that is this right here in the first one. We drew a picture, we found our equation. The next one, we kind of had a picture for us, we wrote our equation. The third one, we did our picture, we did our initial equation, and then we wrote that all in one variable. Number 4, we drew our picture, we established what we were looking for, that equation for the length of wire. We then found those and put them all in one variable.